Welcome back. In this second video on electronic wave functions, we'll focus on the radial component of the wave function and representing how it changes as a function of the distance from the nucleus of the atom in the various orbitals. And we'll discuss radial nodes and the radial distribution function. We'll start, however, with some simpler examples of visualizing orbitals. Hopefully you'll find them simple, beginning with the 1s. Let's begin with the simplest example, the 1s orbital. N is 1, L is 0, m sub L is 0. Shown here is the equation for the wave function of the 1s. The angular component, shown in blue, has no angle dependence, and so the orbital volume is a sphere. The wave function, psi 1s, shown here in green, has its maximum amplitude at the nucleus, and then exponentially decays with r. There are no radial notes. There is no change in the sign of the wave function with distance, nor is there any change in sign with angle, so there are no angular notes. And so there is no change in the sign, the phase of psi with either r or with angle. Now let's take a look at psi squared, the probability density. Again, it has its maximum at the nucleus and decays with r. Now let's turn to the radial distribution function, the RDF. These you will have seen before in freshman chemistry, and are the most common method for representing the change in the probability density with distance. The RDF is a product of the square of the radial component of the wave function, which is the probability density at a point in space, and the area of a spherical shell at that radius. So while r squared decreases from a maximum at the nucleus with r, the surface area of the shell increases with r. And the RDF is the sum of the probabilities at each point in that shell. In other words, it's not just the probability of finding the electron here at this point. It sums the probabilities in that spherical shell and gives the resultant RDF shown in black. So the RDF doesn't actually maximize at the point where r squared is a maximum, but it can be at a slightly different distance. Finally, we have the boundary surface diagram, which encloses the volume where the probability density is 90%. This is actually a fancy version of the BSD, because in addition to showing the shape, my shading also represents the change in the probability density with distance. That's usually not included in the BSDs we often see. Now we will look at the radial distribution functions for different orbitals and see how these change with the values of the principal quantum number n. We'll focus here on the s orbitals with L equals 0, in particular the 1s, 2s, and 3s. The solutions to Schrödinger's wave equation, i.e. the wave functions, are shown here for each of those orbitals. For each one, we notice the angular component is the same. All of the orbitals are spherical symmetric and have no angular dependence. Now let's focus on the differences in their radial components. So the radial component has two parts to it. One is an exponential term, where we see the exponent is varying with 1 over n. As the value of n increases, the exponential decay of the radial component moves to higher and higher r. And this is effectively the size of the orbital. So here in our RDF pictures for the 1s, 2s, and 3s, we see the 1s decays more rapidly than the 2s, or in turn the 3s. And so the 3s orbital is larger. The other term in the radial component is a polynomial in r. And it is this term that introduces radial nodes into the RDF. For the 1s orbital, there is just a constant. There is no dependence on r in this term, and therefore it is a 0-degree polynomial. And as a result, that wave function, the 1s, has no radial nodes. For the 2s, this function is a first-degree polynomial, just varying with r. As a result, the 2s orbital has one radial node, shown here. For the 3s orbital, this polynomial is second degree. It introduces two radial nodes. And so for the 3s, we see the radial nodes here and here. And so there are two key terms in the radial component of the wave function. One affecting size, which is inversely related to n. The second, this polynomial, which introduces radial nodes, the number of nodes just scaling with the degree of that polynomial. The quick way just to evaluate the number of radial nodes, which again you've probably seen in freshman chemistry, is the number of radial nodes is just equal to n minus l minus 1. Now let's go to some pictures, some boundary surface diagrams that represent the existence of the radial nodes in these three wave functions. For the 1s orbital, it has no radial nodes, and so if we draw a boundary surface diagram, there is no change in phase as a function of distance. And so we are just using one color to shade the 1s orbital. The 2s orbital has one radial node, and so at that node, the wave function changes from one sign to the other. For example, from positive to negative, or in this case, from orange to blue, which are the colors representing the two phases. The 3s orbital, here's our picture, a boundary surface diagram. The 3s orbital has two radial nodes, shown here and here. And so now our drawing, if we colorize it to represent the change in phase that accompanies that radial node, we start with one phase. The phase switches across the first radial node, so we go from orange to blue. And then at the second radial node, the phase switches again back to the original phase. To emphasize the change in the sign of psi at each radial node, let's look at the wave functions for the 2s orbital. We know the orbital is spherically symmetric, and it has one radial node. And here I've drawn a boundary surface diagram similar to the ones we just saw for the 2s, where I'm emphasizing the change in the phase at the center. So here I'm saying the phase, the sign of the wave function is perhaps positive, and then it switches at my radial node here, becomes in this case my orange color, or a negative sign. And so here is a plot of the wave function for the 2s orbital. We see, as with the 1s, it has its maximum amplitude at the nucleus, and now we can see the sign change at the radial node. So here is my radial node, my wave function, maximum of the nucleus, decays, and then changes sign in this region, and then eventually tends towards 0. So at this node, I go from positive to negative. I change the sign of the function. Now we'll look at psi squared, the probability density. Because I've squared it, I lose my signs, but I do not lose my radial node. And so now for psi squared, we see at the node there is 0 probability of finding the electron. But on either side of it, of course, we do have probability density. And so psi squared decreases, reaches a node, and then increases a little bit, and then exponentially decays towards 0. Because of the node, there are actually two maxima in psi squared. The radial distribution function, the sum of the probability density over a sphere at R, also has a radial node. Again, it takes a value of 0 at the node, and we have two maxima in the RDF. Here's my first, here's my second, and actually the second peak in the RDF is significantly larger than the first. For the boundary surface diagram, focus on the shape of the wave function, but if we want to provide more detail, we can include that radial node in our shading, as I've done here through a colorized version where I go from a positive to a negative phase. Radial nodes are also present in higher L orbitals. As mentioned before, the number of radial nodes can always be calculated from n minus L minus 1. An easy way to remember this is when a given L orbital is first allowed, it has no radial nodes. And then every subsequent appearance, if you like, of the orbital at higher n, it picks up one extra radial node. So for example, the 2p. There's no 1p orbital. The first time it's allowed is for n equals 2. The first appearance, 2p, it'll have no radial nodes. Then for 3p, it'll have one radial node. 4p, 2. 5p, 3, etc. So here we're comparing the RDFs of the 2p and the 3p. First of all, let's just notice the radial extent of the orbital. Higher n, higher r, decays more gradually. Secondly, the 3p now will have one radial node at which their wave function changes sign. The RDF is 0. And we have two maxima appearing in the RDF for the 3p. Now let's compare three different L orbitals for a given n. Here, the 3s, the 3p, and the 3d. The 3d, first time the d orbitals L equal 2 are allowed is for n equals 3, and so we know the 3d will have no radial nodes. 3p, as we already mentioned, one radial node. 3s, okay, it's the third time the s orbital has appeared. 1s, no nodes. 2s, one node. 3s, two radial nodes, shown here. The other thing to notice is because the n is the same for these three orbitals, their radial extent is also the same. That regardless of the number of radial nodes, they decay to essentially 0 at the same value of r. We also notice for orbitals with multiple radial nodes, the maximum value of the RDF increases with higher r. We'll get to this later when we talk about orbital penetration and electron shielding.